One of the things that an engineer has to know totally is the load in a beam, because beams are the basic building of a structure. As we learned in POE, in starting trusses, you start with a beam. And here's a typical beam, simply supported with a pin on one end and a roller on the other. So you know both of these have a vertical reaction to the downward load of the point load here in order to maintain equilibrium. There has to be a normal force going back up, or a reaction. So for both the concentrated load and for a distributed load, we do have to first of all calculate the reactions at A and the reaction at B in order to then create what we call shear and moment diagrams for this beam. So this is a visual tool that's a graphic solution rather than a formula-like solution that appeals to a lot of students, because not only is it easier just to draw it, but it also gives you a snapshot or a x-ray vision of what's going on inside this beam. You know exactly where the high shear is and exactly where the high moment is just by looking at the picture. So let me go show you the example for these first two. One with a simple beam with a concentrated load in the middle. This would be like one heavy object sitting in the middle of the beam, and then a distributed load, sort of like a roof load or a floor load, that would be in pounds per square foot. In this case, it's pounds per linear foot, so it's 100 pounds per linear foot in this direction. So we're going to go here and we're going to look at the example that I posted for you guys under your 330 beam analysis assignment. The first picture here is my example of how the concentrated load is drawn up. So you notice here you start out with a free body diagram of the load itself. Just a simple line representing the beam, a pin, and a roller. You have the point load as given in the problem as 500 pounds. It's right in the middle, so it's 8 feet from each end. And this is a 16-foot beam. So before we can proceed, we need to know what the reaction at A is and the reaction at B is in order to then draw the shear and the moment diagrams down below, which is a graphic solution. So if you recall from equilibrium, we would have to use the sum of the moments about A in order to calculate the reaction at B. We would have to use the sum of the forces in the y direction to calculate the reaction at A. And I'll leave you to recall that from POE on how you set these equations up. So now once you have the reactions and the loads, then you draw a second line the same length down below it. This will be your shear line, and you follow the vectors. So you follow the reaction up by 250. And again, the scale doesn't really matter, just so it makes sense. You know, like if 500 is twice as long as 250, you use twice as many blocks, right? So we go up, we follow this vector up 250, we stay constant until we hit another vector, and when we hit the 500 vector, we drop by 500, and then we stay constant until we hit another vector, and when we hit this reaction, we go up 250, and you should end up back on the beam. So what this is, if you shade these two rectangles in, what you have is a picture or a snapshot of the shear in this beam, which is positive 250 upward on this side and negative 250 on this side with a 500 shear in the middle. Okay. Now there is a relationship between the shear and the moment. You draw another line down here representing the beam, and to get the moment, the shear value is actually the slope of the moment curve. Now there's a little bit of calculus tied into this. If those of you who studied calculus know that if you take the derivative of a line that defines this line here, the line equation, if you take the derivative of it, you get the slope, and that's kind of what we're doing. So it tells me that the slope of the moment curve is positive. See, this shear is all on the positive side of the line, and it's constant. So we have a constant positive slope. So the way I draw that is I put a dot somewhere at the middle up here, and I draw a constant positive slope going up to it. Doesn't really matter how tall you make it. Over here we have negative shear, all constant negative shear. So I have a constant negative slope going down back to 0 over here. And so when you start out with a flat curve here on the shear, you end up with a slanted or a sloped curve for the moment. It'll look like a really elongated triangle here. Now, how do you get the maximum moment? You find the area of this half of the shear curve, which is a rectangle, which will be 250 times 8, which will give you 2,000 foot-pounds. So that's how we solve the actual point load. Now, the second type of load you're going to come up on is a distributed load that's all the way across 100 pounds per foot. Well, since this is a 16-foot beam, we multiply 16 times 100. We can represent this load as a single load in the middle of 1,600 pounds simply for the purpose of doing the equilibrium equations. After that, we don't use it anymore. We use the distributed. So I'm going to do the same reactions I did before, the same equilibrium equations. Some of the moments about A, some of the forces in the Y direction, and I calculate these two reactions to be 800 and 800. Okay? So once I know that, I'm again going to follow the arrows to create my shear curve. I'm going to follow the reaction force up 800. Now, these little arrows pointing down are all dropping at the rate of 100 pounds per foot. So if I move over 8 feet, I have dropped 800 pounds, right? So I start at 800. I'm going to drop to 0 here. I'm going to move another 8 feet over. I'm going to drop another 800 pounds down to here. Then I'm going to follow the reaction force back up to the beam. So since I started with a flat load here, I have the slanted load here. Again, following the rules of calculus here. Now again, the area of this, the values of the shear curve represent the slope of the moment curve. So you'll notice here, the shear here is positive, but it's getting smaller down to 0. So that represents an arc. It represents a curve shape because what happens, the slope starts out large positive. The slope starts tilting over till it gets to the top. And at the top, it has 0 slope. And then the slope starts negative, a downhill slope, and it starts small and gets larger and larger slope. So what you have is a small negative slope, a little bit larger negative slope, and a larger negative slope at the end. So anytime you have a slanted line, the next curve you draw will be a curve because it's changing, the slope is changing as it goes along, and it'll create this arc or this parabolic curve. Now again, how do you find the maximum moment? You find the area of 1/2 of the shear curve. So this is a right triangle, 1/2 base times height. So it's 1/2 times 800 times 8, which gives you 3,200 foot-pounds. Now, that's the manner in which you calculate both a concentrated and a distributed load. So if you're actually working down through these problems, you'll notice number 3 actually combines a distributed load and a point load. So you're going to do the same thing to get the reactions, but now you're going to end up following the vectors. A reaction goes up, but instead of staying constant, it's actually going to start dropping at 100 pounds per foot until you get to the middle. When you get to the middle, you're going to hit this other point load, so you're going to drop suddenly like falling off a cliff. And then you're going to continue to drop at 100 pounds per foot at an angle until you get to the bottom over here. You're going to follow your reaction back up. So hopefully you guys have some good luck with this shear and moment diagram. Most students really like this once they learn the technique because you can actually figure out what's going on in a beam with very little calculations and mostly just drawings.